Hi, Tim Skell here, Global HVACR Application Engineering Manager. Today we're going to talk about system design, specifically looking at harmonics and standby generators and what level of harmonics is considered acceptable. So we'll kick things off today with a quick refresher on VFD and harmonics. After those brief two slides, we're going to dive into IEEE 519 because you can't really have a harmonics conversation without bringing up IEEE 519. Then we're going to talk about generators, how they work, and then dive into facilities and what levels of harmonics are acceptable for facilities, and then an overall strategy on how to design a system and what levels of harmonics do you really want for both the generator and the facility. What is a VFD? Well, a VFD is an electronic device, variable frequency drive, sometimes known as a variable speed drive, and takes a fixed voltage from the utility, comes into the drive. These are all electronic devices within the drive. So I got my fixed, say, 480 volt, 3-phase, 60 hertz coming in. Got 6 diodes here, so this would be known as a 6-pulse drive. That rectifies the AC. So I've got my AC coming in, gets rectified, which makes all these negative parts go positive, and then hits the DC bus capacitors right here. The DC bus capacitors smooth that out, make a nice fixed DC voltage. And then the back end of the drive, the inverter side, takes this DC and chops it back up into an AC-like waveform. So you may hear the term harmonics referenced on the output side of the drive to try to describe the quality of this waveform. But when you're talking about building harmonics, IEEE 519 harmonics going back to the generator, that has nothing to do with the back end of the drive, and it's all about what's on the front end of the drive. So harmonics get generated based on how the drive is consuming power from the utility. So when it's basically gulping power at the tops of these waveforms in order to charge up the DC bus, that generates the current distortion in the first place, your current harmonics. And then once you've got current harmonics, that creates the voltage distortion, your voltage harmonics. So that's, in a real quick, brief nutshell, what is a VFD and ultimately what's creating the harmonics. If you're interested in more details, there's a lot of presentations out there by ABB and others on actually in more detail how the harmonics are generated. So now if I want to take a look at what does the waveform actually look like for current distortion and voltage distortion, this waveform on the left here is considered current distortion. So a nice, perfect sinusoidal waveform would come up and then back down like this. But this is the classic double hump or bunny ears waveform that you'd see on a 6-pulse drive. This particular drive doesn't have any kind of harmonic mitigation at all. If you started adding reactors, this hump would not come down nearly as low at full load. It would be more along the lines of that. So you can add impedance to mitigate harmonics. There's a lot of different harmonic mitigation solutions. Over here on the right, this is your voltage distortion. So this is a pretty ugly waveform because ideally a voltage would be nice and smooth and rounded up on the tops and bottoms there. This right here is considered flat topping. So this is voltage distortion. This amount of voltage distortion, just as a reference point, is just a hair over 5% voltage distortion. So when you talk about harmonics, the percentages get thrown out a lot in order to kind of compare this waveform to another waveform. So just keep in mind, this right here is a little over 5%, which I would consider to be a pretty poor quality waveform in my facility. So we can't talk about harmonics without talking about IEEE 519. So this presentation, we're really going to be focusing on harmonics and generators. But let's start with IEEE 519 and what that's looking at so you can try to figure out, does IEEE 519 come into play when we're talking about harmonics? Because the easy answer when somebody's designing a building and they want to talk about harmonics, oh, just make sure the building meets IEEE 519 and that should be good enough. And you know what, if you don't have a backup generator, yeah, that is good enough in most cases. However, we got a little wrinkle today because we're talking about facilities that have a backup generator. So looking at IEEE 519, a little bit of history. So it came out in 1981. It was really focused on voltage distortion. And voltage distortion is what a customer, what you in your building, what you care about making sure there's good quality voltage waveform. 1992, they updated IEEE 519 standard to add current distortion targets in there. One of the reasons they had to do this is because if you had multiple customers on the grid and you had one that was a bad actor and was really messing up the power quality, it was hard to determine, hey, who is the problem child here? So what they did is they put specification and requirements in there for current distortion because the current distortion is unique to an individual customer or building where voltage is kind of shared across the entire network. So in 1992, they added that current distortion. Really good idea. Still, there was confusion in the 1992 standard on where you measure harmonics, that point of common coupling. So 2014 came out, they did a better job clarifying the PCC, point of common coupling, on where to measure harmonics, but they really started backing off on the voltage distortion requirements. They made the requirements so high in voltage distortion that they almost became non-applicable, at least from the user point of view. There's still a requirement for utility to get a certain degree of power quality to the customer, but from a user point of view, the voltage distortions are so high that they don't add a whole lot of value anymore. And they did that kind of looking at what IEEE 519 is. It's a utility standard. So the utility doesn't truly care what's going on in your building as long as you're not impacting the utility, the grid, or your neighbors, where the utility is going to get a phone call because customer 3 is complaining about bad power, which is ultimately being caused by customer 1. So IEEE 519 definitely steering towards utility standard the last couple updates, with less concern about what's going on in the building. And then 2022 came out, not major changes from numerical values and things of that nature, but there were some adjustments and a specific clarification when it comes to generators that's going to be very key that we'll talk about today. With IEEE 519, that point of common coupling is a very important topic to understand, because basically what it's saying is, where do you measure harmonics? Where does IEEE 519 apply to? So if we look at it from a definition side of things, quote, the limits in this standard shall apply to the point of common coupling between the system owner operator, i.e. the utility, and a user, i.e. your hospital or water treatment plant, where the point of common coupling is usually taken at the point in the power system closest to the user, where the system owner operator, the utility, can still offer service to other users. So let's take a look at these diagrams here on the right. So I've got my utility, I got my grid right here. Usually when you're talking about harmonics, this ends up coming up in larger buildings, and larger buildings I work with, you're typically dealing with, they have their own dedicated transformer. So I'm going to make the assumption here in this drawing that each building has its own dedicated transformer because it's a larger facility. So I've got customer 1 with its own transformer, customer 2 with its own transformer, customer 3 with its own transformer here. So the point of common coupling is right where these arrows are. It's where the system is closest to the user, where the system owner operator could offer service to other users, which is right where these arrows are, typically the primary side of that transformer. Real world, when folks go out to do measurements, it's a lot safer and easier to say do this on a 480 volt side than it is to do it on a 13.2 kilovolt side. So you'll see measurements taken here, but the standard actually applies to the primary side, in this case for the point of common coupling. So when we talk about generators, understanding this PCC is going to be an important item. So what I'm going to do on the next slide here is we're going to focus just on this customer 3 right here. And then we're going to take a closer look at this PCC and IEEE 519. Okay, here we go. We've got that same customer 3 right here. Same transformer from earlier. And when I'm connected up to the utility grid and getting power from there, my point of common coupling is this green arrow right here. So now let's say my utility power goes out, my automatic transfer switch switches over, and now I'm getting power from my generator. So where is my point of common coupling now? So as a quick reminder, the point of common coupling is between the system owner, utility, and the user. So that's why we had that green arrow here. But now that I'm fed from the generator right here, where is my point of common coupling? I'll pause for a second, let you think about that. I'll give you a hint. The generator isn't feeding back to the grid. We've got our own little island of power source right here. This generator is not going back to the grid. It's not impacting any neighbors. So where is my point of common coupling? Well, the answer is a trick question. There is no point of common coupling in this situation, because when I am connected to my backup generator, I am no longer connected to the grid, so thus there is no point between the system owner and the user, because I'm my own little source right here. So there is no point of common coupling per IEEE 519. So now we have to start asking ourselves, does IEEE 519 apply to when I have a generator as my power source? And I'm going to focus specifically for, say, a hospital, that water treatment facility, large commercial buildings, data centers, anybody who feels like they need to have a backup generator. I'm not talking about somebody who's got solar panels on their roof and they're putting 25-50% of their normal power consumption back onto the grid. I'm looking just at a scenario where I have a generator for my own building as a backup. And does that scenario apply to IEEE 519? Now, some of you who are already experienced with IEEE 519 are going to say, Tim, but what about Table 2 in IEEE 519, specifically Note C? So let's take a look at that. So we've got Table 2, got some nice numerical values here, and we have this subnote C right here that basically says all power generation equipment is limited to these values of current distortion regardless of this value over here. So basically what it's saying is all power generation equipment should have 5% TDD as the target. It's pretty straightforward, right? All power generation equipment. So early on in my career in Harmonics and IEEE 519, that's what I did is I said if you had a generator, you had to have 5% TDD, and I referenced table 2 note C specifically as that reference point. However, that wasn't really the intent of IEEE 519. Remember, IEEE 519 has morphed itself into more of a protect the utility type of a standard, protect the utility from the user, not really necessarily protect the user from themselves. So does the utility really care about a situation where it's a backup generator? So let's take a look at what IEEE 519 did when they updated to the 2022 standard. So I'm going to, in just a moment, I'm going to update that image on the right, and you're going to see pretty much nothing changes up here. So there'll be a little change here in note A. We won't worry about that, but I want you to pay attention to note C. So right now we're at all power generation equipment. I'm about to change it. 3, 2, 1, boom. Right there is IEEE 519 2022. And now what do they say for note C? Power generation facilities are limited to these values. So it's no longer the word equipment here, it's the word facilities. So IEEE 519, their intent is to make sure a power generation facility. So we're talking somebody who's got solar, they got wind, they have another power generation source that they put back onto the grid, thus they can impact their neighbors. That's where note C comes into play. But in the case of my generator for my hospital, my generator for my wastewater treatment facility, I'm not putting any of that generator power back onto the grid. So really, note C and IEEE 519 doesn't apply. So the point of my last 2 slides is to tell you that IEEE 519 does not have a requirement, does not have a standard, ultimately does not care about what your power quality is when you have your building fed from a backup generator, as long as that backup generator is not feeding anybody else. So if you're a consulting engineer and you still want to use that 5% TDD as your target, and that's what you want to specify, hey, there's absolutely nothing wrong with that, but you just need to be very crystal clear in your specification. You're not doing this because of IEEE 519 for your 5% TDD. You're doing it because that's your design approach to what level you want to limit the harmonics to. So again, IEEE 519 does not care about when you have a backup standby generator. And that's one of the main messages I want you to take away from the last couple slides, because then it really comes down to is, well, if I can't reference IEEE 519, well, then what am I supposed to do when I'm looking at harmonic levels and a backup or standby generator? Before I answer that question, let's take a look at how does a generator work. You may have heard the term AVR, one of those acronyms for automatic voltage regulator, or just simply a voltage regulator. That's really the brains of your generator. So I've got a real simple block diagram here of how a generator's alternator system works, just to kind of go through some of the main parts here. So we've got a power source, permanent magnet generator is feeding voltage to that automatic voltage regulator. That just makes sure it stays power up. So any of your larger commercial grade generators are going to have this. This isn't the 2 kilowatt generator you got up north at your cabin or something like this. This is more of a characteristic of a larger generator. So you got your PMG feeding your AVR right here. And what this automatic voltage regulator does is it's looking at the output of the generator. So just view this as the output of the generator. And it's trying to make sure the generator is having that appropriate voltage magnitude and appropriate voltage frequency. So say, for example, 480 volts, 60 hertz, or 400 volts, 50 hertz. So the automatic voltage regulator, AVR, is responsible for making sure you've got that perfect voltage magnitude and frequency. So how it does that is it looks at what's going on. Either it could be looking at single phase or all 3 legs, or the 2 legs or all 3 legs. And then what it does is it controls the generator by sending a signal out to this exciter field right here. And then the exciter field controls this overall rotating assembly by controlling the exciter and the main field rotor right there. And then this part here ends up providing the output to the 3-phase out to your building here through the main armature. So the takeaway and the reason I'm showing you this is I want you to understand that this automatic voltage regulator, AVR, is very important for the generator to function appropriately. And the way it works is it's working by looking at what the output waveform is coming out of the generator and going to the building. So let's say I've got some harmonics. What does that really do to the generator? So I just said that AVR is looking at the output of the generator and is trying to maintain a fixed frequency such as 60 hertz. Well, it's sitting here looking at the zero crossing, and if you look closely here, well, there's a lot of harmonics. This is high frequency harmonics in this particular example here, and it actually crosses the zero crossing multiple times. So when it looks at the zero crossing, really the generator is expecting it to cross this point just once over here, once over here, once over here, and that's how it figures out the frequency. But if it's crossing multiple times, which is the right one? So when you've got this fuzziness on the waveform from harmonics causing the multiple zero crossings to occur, it's really hard for the generator to estimate what is the output frequency at that given moment, because it doesn't really know which part of the waveform to look at. So if I really zoom in at that waveform and I look at that zero crossing, I can see 1, 2, 3 different times that wave has crossed the zero voltage point. So which one should that AVR use as part of its calculations? That's one of the reasons why it's really challenging when there's harmonics, especially high frequency like this, on the load for the generator to function appropriately. So what ends up happening is it has to kind of guess which is the right one. So you can adjust your PID loops, you can adjust filtering. There's a lot of different approaches that the generator manufacturers can take, but it's always a challenge. And the more zero crossings, the more noise you've got there, the harder it is on that generator. So what happens when things get out of whack? So the generator is sitting there constantly trying to maintain, say, for example, that 60 hertz, and it's seeing 59.9, 59, 61 because it's picking the wrong zero crossing. Now your generator starts to surge, starts to hunt. You actually hear it speeding up, speeding down, slowing down. Speeds up too high, the generator will just flat out trip offline to protect itself from failure due to overspeed operation. So the generator, ultimately, worst case, will trip offline if there's too much harmonics on that particular power feed to the building. Other concerns regarding harmonics and generators, well, harmonic currents that things like drives, your nonlinear loads are all consuming, well, that takes up some of the generator capacity. So the more nonlinear load you've got, the more nonlinear current draw you've got, the more almost, I don't want to call it wasted, but it's excess energy that the generator's got to produce that really doesn't have any practical use. So you've got the harmonic currents are consuming some of that generator's capacity. Also, harmonics just create heat in generators. One of the negatives of harmonics is you heat in transformers. Well, you've got the same thing going on when you got generators. So then you end up having to size the generator larger in order to deal with the heat in order to produce those current harmonics. And then another thing you gotta watch is making sure that you keep the harmonic levels to the point where the generator manufacturer can accept. So you get harmonics that are too high, just like we talked on the previous slide. You can end up having the generator tripping offline. So you gotta make sure that you keep harmonics to a level that makes the generator, I'm gonna call it happy. And this, we're gonna talk a little bit later about weak links. Basically, there's going to be 2 weak links you got to consider. The generator is one of those weak links, and we'll get into that. And lastly, don't forget about power factor. So when we talk about harmonics, immediately people start thinking, well, how do I fix harmonics, Tim? How do I clean them up? Well, there's things you can do like adding passive harmonic filters in front of drives, for example, to clean up harmonics. Some of those solutions have some negatives to them, like leading power factor. So if I look here on the right here in this diagram, this side here is lagging power factor. This is leading. So as I'm more loaded, so as I follow this line out here, if I'm in a leading power factor situation, it becomes unstable for the generator. Generators like to have lagging power factor, not too much lagging, keep it above 0.8 in this example, but they want to have good quality, slightly lagging power factors, the preference for a generator. So if you have harmonic mitigation solutions that push power factors leading because of the capacitors in them, that could be bad for the generator operating condition. So a couple different things you keep in mind when you're dealing with generators and harmonics. We'll take a step back from talking about generators now and focus a little bit more on the building, your facility. Doesn't matter, again, hospital, water treatment facility, doesn't matter what building we're talking about. Harmonics are fairly universal. It's well known some of the negatives of harmonics as far as what they do as far as equipment failure or excess heat generation. If you're not overly familiar with some of those things as far as the negatives of harmonics, check out the Harmonics and HVAC applications app guide that we've got. Scan that QR code in the top right corner and it'll take you to it. So if we kind of look at our steady state operating condition of our building, we know our facility cares about voltage distortion. We want good quality voltage waveform. We care about current distortion. The lower the amount of current that I'm drawing, the smaller my wire sizes can be. And then of course, IEEE 519 is all about TDD as far as what the targets are. But when I take a look at my short-term operation, I'm going to run this way for 6 hours because the power went out and it's just going to take a while for the utility to get back up and running. I really don't care so much about current distortion in that case. from a building power quality aspect, I'm really concerned about the voltage waveform quality, because that's what my equipment cares about, is how good is my voltage waveform. So in that short-term operating mode, I'm going to really focus on voltage distortion as my concern and what I'm designing my system for. So now the big question, the $1 million question, is what level of distortion is acceptable for my facility? And while the answer is it depends. What type of facility am I? Hospital, office, water treatment? Do I have some sort of labs that I need to have equipment that has really precise measuring 24/7, data center, a lot of different types of buildings? And then once I consider my building and kind of what I want for power quality in that building, what are my expectations? Because let's face it, if I'm a hospital, I want good quality power. If I'm a general office building, you know what? If I could go a couple hours on generator power, my power quality is not quite as great. Not a big deal. But then, and a big part of this is considering that short-term versus long-term is in a worst-case condition, and I'm on generator power for an extended period of time, how good do I need my power quality to be? Again, depends on the type of customer I am. If I'm a hospital, it doesn't really matter if I'm on generator power for 30 minutes or 30 days. I'm going to want good power quality the entire time. Again, office building, if I'm just short term, I can probably handle a little extra distortion on there. So now you say, Tim, what are some percentages? What are some good numbers for me to keep in mind for designing a system? What is a good starting point? Well, I'm going to kind of point back to IEEE 519, 1992. So if you remember back when I was talking about the history of IEEE 519, 1992, in my eyes, and granted, my opinion, is the last time IEEE 519 truly cared about it from a user facility viewpoint before they really made it heavily to protect the utility grid. So they had a table 10.2 that talked about voltage distortion, and it went based on the type of building you were. So they had something they considered special applications. So if you look here on the right, you'll see that special applications had a target of 3% voltage distortion. So they gave some examples of hospitals and airports as special applications. You've got your general system, that would be more of your typical office building for 5% voltage distortion. And then dedicated system would be, say, a factory, and you're just able to handle it in the factory. So I don't really, 10% to me, in my eyes, is just absolutely ugly. I wouldn't even talk about that, but that 3 to 5% at least gives you a good range. I would say a lot of power quality experts I've talked to, and the ones that are out there going out in the field and trying to solve power quality issues where there's a problem going on out there, they would rather see your voltage distortion be less than 3%, stay 2% range. But this just gets you that starting point. So now, I mentioned weak link earlier. So the facility is essentially one of those items I'm going to consider a weak link. You've got a generator and its requirements, and you got a facility and its requirements. So I want you to keep that in mind when we start talking about system design in a moment. Let's take a look at this weakest link concept now. So we're going to consider the generator power scenario. I'm not worried about the utility. Again, utility's got IEEE 519 to tell you what the levels need to be. But my generator mode, that short-term generator mode, I got to figure out what is my weakest link. Is it the generator's capability, or is my facility's need? Which of those two is more stringent, needs to have better power quality? Is it the generator capability, or is it my facility? And if you're expecting me just to give you a one-size-fits-all answer, guess what? There's no one-size-fits answer. Because remember, depending on your facility, am I a hospital or an office building? Those two type of buildings have different power quality needs. And then you got the generators. There isn't just one manufacturer of generators. There's a lot of manufacturers of generators, and then they have different designs for their generators on what their capabilities are. So it's really matching the right equipment for the building that you have. So let's take a look at an example. Let's say I've got a generator, and I talk to my generator manufacturer, and I say, hey, what level of harmonics can you tolerate with your AVR before you're going to be worried about having that generator have to trip offline and have power problems from the generator? And let's say the generator manufacturer's got a nice robust one, and they're not all at this level, but let's say they can do 10% voltage distortion before they have a problem. Hey, okay, that's a good number to have, so I've got that number. Now I'm looking at my building. Let's say it's a hospital. Well, my hospital, I might have somebody in the OR. When the power goes out, I'm not going to stop working on them. I need to have good quality power for my sensitive equipment in the OR. So I'm going to say that I want no worse than 3% voltage distortion. So I want 3% or better for that hospital. So now I'm doing my system design. I got a generator that can handle 10% voltage distortion, but my building needs to have 3% voltage distortion. How should I do my design? Well, my design should be to the weakest link, which in this case is the 3% requirement of the hospital. Generator can handle 10% voltage distortion. Hey, that's good to go. I don't care about that at this point. I need to design my system to keep the harmonics at 3% or less because that's what my facility needs. I'm designing it to the most stringent value. And again, I know I'm throwing percentages out there, so I grabbed a couple waveforms here just to share with you on the right. This top waveform right here, again, voltage distortion, one of the things you can look at is the flat topping here. This waveform here is 4.5%. This waveform here doesn't have quite the flat topping out, a little bit more rounded, is 3%. So again, when we start talking about all these different percentages and what power quality and what it really means, here's a couple of good examples for you just to help illustrate what is 4.5% voltage distortion versus 3.2. So this generator in this example can handle 10%. This is going to be a lot flatter than right here if it's 10% voltage distortion. So it tells me it's a good generator to handle that, but that's not really what I want for my hospital, wanting 3%. The other thing to keep in mind in this is when you pick out a generator, I may want 3% for my building, but a lot of generators, they might only create a power waveform in the first place that is only roughly this good. They might have specs that say, hey, I'm only good up, I can provide a waveform as clean as 5% voltage distortion, or I'll keep it below 5%. So definitely need to coordinate with your generator vendor to make sure that they can get the quality of waveform down to the levels that you need. And so it's not just what they can handle from a distortion before the generator has problems. Can the generator create the waveform in the first place that you want? So there's a couple different angles you need to look at here. So let's take a look at the strategy here and look at where and how a harmonic analysis comes into play. So you want to do a harmonic analysis on both the utility and the generator power. I think I've beaten that horse pretty good here as far as IEEE 519 cares about utility. So you need to do a harmonic analysis based on utility power, its transformer size, things of that nature to make sure that you meet the IEEE 519 guidelines. And then we need to do a separate analysis on generator power. So transformers and generators are definitely not the same when it comes to a harmonic analysis. So what I did just to illustrate that is, let's say I got 400 horsepower of 6-pulse drives with impedance. So in ABB speak, these would be ACH 580 drives, 400 horsepower, typical transformer size, 1500 kVA, 5.75% impedance. And let's say my backup generator was also the equivalent of 1500 kVA, which would be 1200 kilowatts if we were dealing with a 0.8 power factor and a 0.20 subtransient reactance, just kind of giving us a baseline. So some assumptions here to try to do an apples to apples comparison. I took this exact same load of 400 horsepower 6-pulse drives. When I do the analysis based on the transformer, my voltage distortion for my building was 2.75%. That's the secondary side of that transformer. So my building power quality, hey, I'm good to go there. However, I take that exact same group of drives, and when I put it on this generator right here, my harmonic voltage distortion is now 7.4%, which is a lot worse, obviously, and something I probably wouldn't want to have in my building. The harmonic distortion is definitely dependent on the stiffness of the power source. So you'll see here that the transformer is a lower impedance, meaning it's a stiffer, a stronger line of 5.75%, where here I was dealing with a 0.20 subtransient reactance, so good 3+ times greater in impedance right there. The other variable in all of this, and again, there's never no easy answer, right? For the system designers, for the consulting engineers out there, you also have to be aware of ECM loads, or really any load that uses thin film capacitors or any device that creates higher order harmonics. So a lot of ECMs out there use the thin film caps, which makes their current distortion look lower, but it's at a higher frequency spectrum. And when you have a higher frequency current distortion spectrum, it really messes up your voltage quality of that waveform. So I can have two devices that are both 30% THDI on the current harmonics, one being a VFD, one being an ECM, but that ECM is going to make a much bigger impact on your voltage distortion. So that's becoming a bigger and bigger deal as you see more ECMs out there. So again, ECMs and VFDs are not created equal. It may look like that when you look at THDI, current distortion, but voltage distortion, which is what the building cares about, ECMs have a bigger impact. So something to keep in mind. Now I'd like to take a look at what do we do once we've done our weakest link, we've figured out what level of harmonics I need to design my building for when I'm in generator mode, and utility mode 2 is part of IEEE 519. I've done my harmonic analysis and I've started looking at the results, and I realized, you know what, I need to do something. Maybe I'm okay on the utility side of things, or I'm borderline on the utility side of things, but my power quality, my voltage distortion is just horrible when I'm on gen power. So what do I do? So step one is I can oversize the generator. When you oversize the generator, that generator becomes a stiffer source. It's a stronger, more robust voltage line, so it's harder to distort that voltage waveform when I have an oversized generator. Also, when you have the generators oversized, it can help handle some of that heating impact of the current distortion aspect. So it's definitely an approach. It's usually considered the more expensive approach because you're upsizing the generator significantly in order to compensate for the fact you're trying to use lower cost drives, and you do the cost analysis, and it's really a loss by just solely upsizing the generator. So the next approach is to add harmonic mitigation to the drives. So usually this is viewed as the better solution because it cleans up the harmonics both in your normal utility mode, so it makes IEEE 519 happy, but it cleans up the harmonics for your generator power scenario too. So it's really a win-win situation. So this image here on the right, I'm just depicting, these are 6-pulse drives right here. These are known as active front end drives right here. It's not to scale, but you can see that these drives are just a little bit deeper than these drives here, and a little bit taller and wider, not a whole lot, but a little bit, in order to fit in that extra harmonic mitigation requirements of an active front end drive. So it's still 3 wires in, 3 wires out, not any extra filters and things like that you have to deal with, but that's definitely an opportunity, is to you add harmonic mitigation. It doesn't have to be active front end drives. There's passive filters, there's adding extra impedance. It's really, you do the harmonic analysis, figure out what makes sense for your building, your application. I did want to mention, though, that there is sometimes kind of a best of both worlds. You kind of mix and match a little bit. Now, it requires you to know exactly who your generator vendor is going to be and to coordinate with them. But what you can do is upsize the generator just a little bit. One of those things where you bump up the alternator size, but don't necessarily need to upsize the engine size, which is where your bigger cost is at. So you upsize your generator a hair, and then you do the harmonic mitigation from there with that little bit larger generator. So it's not, that approach isn't taken very often, but if you're trying to really do some value engineering and get the absolute lowest cost sweet spot, that's an approach you can take. So let's take a moment, let's bring it all together and kind of have a conclusion of what we talked about. So again, harmonics, IEEE 519 is always brought up as like, oh, just do IEEE 519. And again, I convinced everybody that IEEE 519, well, it's great when you're on utility power and there's some requirements there to make sure that your building isn't going to impact the grid. It doesn't apply when you have a standby generator. So this means that the system design, that responsibility falls on the consulting engineer to figure out what harmonic mitigation does my building need when I'm on generator power. Because I got to make sure the generator's happy. I need to make sure the building's happy. And when I'm making those considerations, I'm basically taking the weakest link, and I'm also taking in the fact that, you know what does my building power quality need to be when I'm on the short-term power of the generator? Because I might be willing to accept a little extra harmonics for 30 minutes here or a couple hours there and be okay in my building for a typical commercial building. So you don't need to be as stringent in some cases with a generator, as long as the generator can tolerate that level. Harmonics doesn't cause problems with the generator. So that's why it's just so important to figure out what is your weakest link. Is it your facilities need, or is it your generator need? Once you know that, the rest of it's simple and straightforward. You just need to pick out the product in order to get the harmonics to the level of what that weakest link requires. And there's a lot of different harmonic mitigation techniques out there. I didn't go into great detail here. I mentioned passive filter, active front ends. There's a lot of content out there. If you need more information on that, just reach out to your local ABB representative. They can get you details on the different hardware solutions out there. And then lastly, if you're the type of person who wants to look back at this topic 6 months, a year, 3 years from now, but you don't want to sit there and listen to me talk for 40 minutes, well, go check out ABB Technical Note 127. Go ahead and Google that, backup generators and harmonic levels. It's a write-up that's similar to the concept that was covered here in this presentation, and it'll give you that quick refresher of those recommendations. And with that, I'd like to thank you for your time.